Hello everyone, I'm Jiahao Zhang Yang from Taiwan. I'm an assistant professor at National Science University. Today it's my pleasure to share our work on the flowering phenology in Fushan subtropical rainforest. In this study, we use long-term flowering data and weather data to evaluate the potential proximate cues of flowering in this subtropical rainforest. Identifying the climate triggers of flowering onset is crucial for us to understand how plants respond to climatic variation and how they time their critical life history events to appropriate seasons. In temperate and boreal latitudes, temperature is generally considered the most critical environmental signal for flowering. Warmer temperatures in spring has been associated with flower development, while cooler temperature in winter is linked to the dormancy of flower buds. In tropics, other environmental variables are proposed as proximate cues of flowering. Low temperature and drought may together trigger the general flowering events in Malaysia rainforest, as demonstrated by Yu's work. Zhou's work in Panama also suggests that seasonal variation in solar irradiance is critical for many tropical species to time their flower events. Some studies also propose photoperiods as an environmental cues of flowering in both tropical and temperate forests. Long-term phenological records are very rare in subtropical area. It's not clear what the major proximate cues of flowering are in this region. Thus, in this study, we would like to investigate what climate variable trigger the onset of flowering in subtropical rainforests using the long-term data from Fushan. Our study was carried out in the Fushan forest dynamics plot situated at the northeastern of Taiwan. The latitude is 24.5 degrees north. The elevation of Fushan is about 600 meters. Annual rainfall is more than 4,000 millimeters with no dry season, supporting an evergreen broadleaf forest. Annual mean temperature in Fushan is 80 degrees C with clear seasonality. Solar year radius, the red line in the top figure, has a similar seasonality like temperature peaking in July, but the seasonality is less strong compared with temperature. Seasonal variation in rainfall is strongly associated with typhoons, which contribute to high rainfall from July to September. We set up 106 traps to monitor the flowering and fruiting phenology in the Fushan forest. All the traps work census weekly since September 2002. In this study, we use data from September 2002 to November 2021, including 997 weekly censuses. We select species with more than 500 flower records, appeared in more than 10 traps in at least 10 years. A total of 16 species met this criterion, including 10 canopy trees, 4 subcanopy trees, and 1 shrubs and 1 liana. Most studied species flower every year during the study period, except cinnamon and myrcene, which did not flower in a few years. We estimate the first flowering days for each species by calculating the median first census that traps record flowers in each species' specific phenological year. This figure shows the total flower records of each calendar day during a 19-year study period for each species. The colorful open circle represents median first flowering censuses for 19 years. We find that the early flowering species tend to have large interannual variation in their first flowering days compared with the late flowering species. Except the only liana species, the interannual variation in first flowering days was negatively correlated with the first flowering days. Following Joe's 2018 biotropical paper, we construct phenomenological model to evaluate several proximate cues of flowering. The simplest model is the phenomenological model. Since the seasonal variation in day length is constant among years, the best estimate of first flowering date in this model is the mean FFD during the study period. The photoperiod model can also serve as a base model among all proximate cues we evaluated. For the model concerning solar irradiance, warm temperature, and rainfall, two stages of flower development were considered. The first stage is floral induction, which begins after an environmental signal accumulated over NE days exceeds a threshold first time in a year. The second stage is floral development, in which flowers take ND days to develop after floral induction. And two types environmental signal were evaluated. The first is the mean level of the environmental signal, and the second is the directional change in climatic variables. We use grid search approach to estimate parameter value of each phenomenological model for more than 1.3 million parameter combinations were evaluated for each model. We evaluate each parameter combination by calculating the loop mean square errors between predict and observed FFDs. For RMSE values less than 1.5, we took that as a strong evidence for that parameter combinations, and RMSE values greater than 2 as a weak evidence. Here's the results. RMSE value of the photoperiod model actually equal to the standard deviation of the FFD. The species with large interannual variation in FFDs would have large RMSE values. Among the other 7 models, temperature hypothesis best predict the FFDs of certain species with lower minimum RMSE values than the photoperiod models. Irradiance had higher RMSE value than temperature model and were 1.5 larger than 1.5 for most species, and only one species had lowest minimum RMSE values for the irradiance model. Rainfall model failed to explain the variation in FFDs in any species. Most of the RMSE value were larger than 4. Let's take a look of the estimate parameters. For the early flowering species like Machilus sambergi, it flower in March, and cooler temperature model best predict its flowering times. Its ND equals 68 and NE equals 90, which means that its flowering time were sensitive to the cool temperature in last fall and winter. For late flowering species like Lycia acuminata, it flower in July, except the photoperiod model. The warm temperature best predict its flowering times. Its ND equals 20 and NE equals 90, and which means that it would flower after 3 to 4 months of consistently warm temperatures. To conclude, early flowering species had a higher interannual variation in FFD than late flowering species. This might be due to the large variation in environmental signal they experience. Early flowering species were sensitive to the temperature variation in last fall and winter, while late flowering species flower after 2 to 4 months of consistently warm temperature. Seasonal variation in temperature, irradiance, day length may co-determine the flowering times in Fushan. We appreciate the long-term funding support from Ministries of Science and Technology in Taiwan, Taiwan Forest Bureau, and Taiwan Forestry Research Institute. We also thank the logistics support from the Fushan Research Center. And this work would not be possible without the help from our research team and many student volunteers. Thanks for your attention.